Good morning. Hey, let's look at 9-7 on this fine snowy morning. And I want to do a second day on 9-7. You do not have these notes, so you might want to print them. I'll include them in Schoology so you can print this off. Otherwise, it's really not that bad to write on just a sheet of paper. I got 4 problems that we're going to go through, and let me show you what that looks like. It's 2 of those, oops, and 2 of these. So really not too bad. If you just want to jot it down, you can do that too. All right, I want to show you how you can modify off of Maclaurin polynomials that you already know. Yesterday we worked on establishing e to the x. So what I know is that e to the x is approximated, I'm going to do a 4th degree polynomial, Taylor polynomial centered at 0. And that pattern goes 1 plus x squared divided by 2 factorial plus x to the 3rd over 3 factorial plus x to the 4th over 4 factorial. Okay, nice easy one to remember. We want to take and modify and build a new function quite similar to e to the x, only ours is e to the 3x. So I can build this and modify what I know very easily. It's going to look like 1 plus x. Oops, wherever I see x, I'm going to insert 3x. And then plus, I'll square it, divide by 2. So 3x is replacing that x. I'll replace this x, and I'll replace this x. I'm just going to do it right now so I can keep the same color pen. So I'm going to replace this x. I'll get 3x getting cubed over 3 factorial plus 3x raised to the 4th over 4 factorial. How easy is that? Rather than having to go through and do all the derivative work for it again. It would turn out to be the same, but it's just a lot more work that way. So build off of what you know. Then I would just expand this and call it 9x squared over 2 factorial plus 27x cubed over 3 factorial plus 81 x to the 4th over 4 factorial. I'm sure there's some simplifications. I'm sure there are. Well, I can see that there is. Like this would be 6 because 3 factorial. So obviously we could reduce this down and do some simplifying. But only do that if you need to match up like on a multiple choice, okay? Next problem. I've got x squared sine of x, and I want a 5th degree Maclaurin, so that means it's centered at 0. Our c value would equal 0 since we're going to center at 0. What I notice is sine of x is involved here, and I know a pattern for sine of x. So let's build off of what we know. And I would do this on the AP test as well. I would just write, hey, I know what sine of x is. It can be approximated by a 5th degree polynomial, and that would look like, okay, sine, I got to think for a moment. Sine is an odd function. Oh, that's right. These were all odd powers then, as well as being alternating degrees. I'm sorry, alternating positive, negative. So odd powers with alternation. So there's my 5th degree Taylor polynomial centered at 0. Next, let's modify. Well, the modification on this is actually pretty easy. What I want to do is I want to take and multiply by x squared of sine of x. But for sine of x, I can substitute that. So what will happen here is I can do this approximation, still going to be a 5th degree approximation, and I'm going to take my x squared and multiply it through the Taylor approximation for sine of x. And I will end up with a polynomial, won't I? So now let's just distribute. and we'll have x to the third minus x to the fifth over 3 factorial plus x to the seventh. Add those exponents, 5 factorial. There is our fifth degree Maclaurin polynomial approximation. Pretty easy, huh? So I wanted you to see a couple of those easy ones that you weren't rebuilding it from scratch, getting the derivative stuff laid out. However, on the next problem, I will require that we go through the motions. This one's going to take a little bit of paper and a little bit of work. I want us to find a fourth degree Taylor centered at 0. So our n will equal 4. Our c is going to be 2. Now, if you recall, a Taylor's expansion looks like the following. Hang on, I'm getting... Okay, let's see. We were working on the Taylors. So n equals 0 to infinity, and this is where we do that derivative, the nth derivative evaluated at x, or actually c, isn't it? Let's put c in there, at the centering point, divided by n factorial, and then it is multiplied by x minus c, the centering point, to the nth power. So this is the pattern we're going to follow. Well, obviously then we need the derivative. So that's the first thing I'm going to work on calculating, is that derivative. Here we go. So f0 of x, well, the zeroth derivative is the function I'm looking at, so x plus 1 to the negative 1. F prime of x, the first derivative would be negative. X plus 1 to this negative 2. Chain rule would say times 1, so don't really need to write that. That would look like negative 1 over x plus 1 squared. F double prime of x is going to be a positive. Oh, this looks like it's going to be an alternating series. So 2 times x plus 1 to the negative 3. That'll be a 2 over x plus 1 cubed. Triple of x. Negative 3 times 2 is negative 6. X plus 1 to the negative 4. Okay, that'll look like negative 6 over x plus 1 to the fourth degree. And I can stop on that one because... Oh, no, I can't. That was only 3. I was picking up the fourth degree, but we need a fourth derivative to get a fourth polynomial because I need the n up here to be a fourth power. So one more step. How about positive 24 x plus 1 to the negative fifth, which creates 24 over x plus 1 to the fifth. All right, now what we got to do is evaluate this at 2, since that's our centering point, because I need it evaluated at C. And that's going to generate, where am I at? Oh, this would have been 1 over x plus 1. So that's going to create 1 over 2 plus 1 is 3. F prime of 2 would be negative 1 over 3 getting squared, so negative 1/9. F double prime of 2 is going to be, I'm going to find it right there. So I'm going to have a 2 over 3 cubed, so 27. The next one, F triple, evaluated at 2, will be negative 6 over an 81, which would reduce because 3 goes into both of them, so I have a negative 2 over 27. And finally, the fourth derivative evaluated at 2 would be a 24 over a 243. Well, those digits add up to 9. That's divisible by 3. Top digits add up to 6. That's divisible by 3. So let's reduce by 3 and get 81. I'm sorry, 8 over 81. All right, we got those. Now it's time to lay out the polynomial. And I am going to run out of room. So I tell you what I'm going to do. Hang on a minute. I'm going to move things around. Okay, I am ready. Move some things around, deleted some stuff, so that should help me here. All right, so let's go back to a blue pen here. What I need to do is the Taylor expansion, and I'm going to lay it out very thoroughly here. So we're going to go 1 over x plus 1, which we want to find the fourth degree, so it's going to be approximated by a p sub 4 at x. And I'll do this, but you wouldn't necessarily have to do this. I'm going to have the 0th degree evaluated at 2 over 0 factorial, and it'll be x minus 2 to the 0 power. That would be when n was 0. Now let's step this up a notch. Let's move to 1. So it'll be plus the first derivative evaluated at c, which is 2, over 1 factorial, and it'll be x minus c, or x minus 2 to the first degree, plus second derivative evaluating at 2 over 2 factorial, there's this coefficient work, x minus 2 squared. Fit one more of these in, f triple evaluated at 2 over 3 factorial. Get the picture on this, to the third power. And finally, okay, let me do a little magic here, see if I can shrink this down so I can fit one more in. Plus f fourth derivative evaluated at 2 over 4 factorial x minus 2 to the fourth. That's just expanding based on the Taylor recipe. All right, so that turns out to be, now I'm going to refer to the green print where we have our stuff laid out. The 0th derivative, really we're evaluating the function at 2, so 1/3. 0 factorial is a 1, this 0 power is 1, so plus onto the first derivative, that is a negative 1/9 divided by 1 factorial, which is just 1, and then x minus 2. Next one, I have a positive 2/7 for my second derivative. That's going to get divided by 2 factorial. And then multiplied by x minus 2 to the second. The next one is a negative. I pick up negative 2/27, x minus 2 to the third, and that was over a 3 factorial. Plus, final fourth derivative was 8 over 81, x minus 2 raised to the fourth. We know we've got a fourth degree now, over 4 factorial. And then I probably can do a little bit of simplifying. Oh, yay, huh? Because it looks a little rough right now. So I get 1/3 minus 1/9, x minus 2. Dividing by 2 factorial would be like multiplying by 1 over 2. So I'd have 2/27 times, this would be over 1. That would be a 1 over 2 there. Those 2's are going to cancel out, x minus 2 squared. Okay, minus, this will be 2/27. 3 factorial is the same thing as 6, so turn it into multiplication. 2 goes into 6 3 times. I'll come back on my next line and simplify. X minus 2 to the third plus 8 over 81 times 1 over 4 factorial is 24. X minus 2 to the fourth. Alrighty, let's do a sweep here. I'm going to have 1/3 minus 1/9 x minus 2 to the first plus 1 over 27 x minus 2 to the second minus 1 over 81 x minus 2 to the third plus 8 goes into 24 3 times. There'll be a 1 over 243 x minus 2 to the fourth. Hey, not bad. We got it. There's our fourth degree Taylor polynomial centered at 2. It would be actually pretty easy to write this in a simplified summation format where we could have, well, I see 1 on top always, so I'd have 1 over, I see powers of 3, so 3 to some power. If I start my n at 1, I would be on right away. And then I want x minus 2. This was an x minus 2 to the 0 power, wasn't it? So that I can make n. You know what? I'm going to back this down to 0, and then I'll add 1 to that. That would get me on sequence then. Yeah, not too bad to write a simplified summation expansion for this. This would give me an infinite series if I wanted it. I'm trying to make an not too successful in infinity sign there. All right, moving on. Last thing won't take near as long. I just thought it was good to do number 3 and show you another expansion, but at a centering that's not 0. Number 4 here, suppose that the function f of x is approximated by a 6th degree Taylor polynomial. Give the value of each. So part A says what was f of 0, and then part B says what was f triple prime of 0. Well, in this expansion for Taylors, we have the nth derivative evaluated at some value c divided by n factorial. And then I get the x minus c to the nth power. But what's important is right here, this creates the coefficient that we see in front of those degreed terms. So I'm going to take my coefficient and set it equal to this expression. And back over here. So I want really the 0th derivative evaluated at 0 over 0 factorial, building that there. That would have to equal, is there a term for x sub 0? This is x sub 1. So the x sub 0 term must not exist, huh? So I would set this equal to 0. And that is 1. If I multiply up, it looks like the original function, because remember, a 0th derivative is the original function. This f of 0 equals 0. Hey, one other thing. How did we know this was 0? How come I could evaluate that at 0? Well, when I look at this Taylor polynomial and I see x to the third, that was built off of this. C had to have been 0. This truly really was a Maclaurin polynomial, because these would have been x minus 0 to the 6th expansion. Okay, so that's why they're asking us to find f at 0, or f triple prime, because the derivative would have been evaluated at 0. All right, triple prime. That means my third derivative evaluated at 0 divided by, now n was 3 factorial, must equal, oops, better grab the negative, huh? Must equal -4, the coefficient in front of the x to the third term. Multiply up by 3 factorial, and I have the third derivative evaluated at 0 is -4 times 3 factorial, but 3 factorial is 6, so this would turn out to be -24. Perfect. All right, homework. I don't know that I have the homework sitting in here, but I'm going to post the homework for you. It is out of a different textbook, so you'll want to print it. Thank you.